Welcome again, Trinity Classical Academy, to watching Mr. Bourgeois doodle on a whiteboard app. I hope and pray that this quarantine period finds you well. This is really a lot like a zombie movie, not gonna lie. I've watched quite a few end of the world, apocalyptic, post-apocalyptic zombie movies, and this really feels like it in a lot of ways. So I'm really excited to be a part of history and what God is doing. So, in a lot of ways, it's very much not like zombie movies at all, because, I mean, let's face it, there's a lot of stuff in there that probably is not going to happen. It's okay. But I want you guys to take a look at your book. I'm not talking about the content of your book, but the physical book itself. Look at its construction. If you're open to page 120 and you look down the spine, you'll see it looks something like this, right? Like, there's a bunch of pages that go out like this. Yoink, yoink. Like the part of a person's hair, right? And then there's the cover like this. The little nubbins like that. I want to ask you, consider how much volume your book is taking up right now. How much space are these papers and this hardcover binding backing? How much is it taking up right now? And then shut the book. Shut the book. And then look at the cover of it. This is the cover, right? Math and stuff. Math and stuff. So the cover of your book is a rectangle. Now look at the stack of paper that your closed book is. How much volume is that taking up? Probably a better example to demonstrate what I'm talking about is supposing we have a sheet of paper, all right? This is what it looks like from the bird's eye view, and this is kind of what it looks like horizontally. Well, let's try that again. This is what it looks like horizontally. Your book is really a whole bunch of stacks of paper. There's sheets of paper on top of sheets of paper on top of sheets of paper. When we measure the area of a square or a rectangle, we take the length times the width, right? And that tells us, okay, it's so many square centimeters, or you could say hectares if you're being weird. Anything that measures area measures that. Now, when we talk about volume, well, when we have volume, we're adding a third dimension, right? I mentioned in my stint in the finance world, with stock options, which are crazy right now, you have a four-dimensional chart that you have to make in order to predict the different variables. There's one dependent variable and four independent variables, so you have a four-dimensional chart, and how that's really hard to do. We live in 3 dimensions, so 3 dimensions is easy to do. So imagine you have this width and this length, and now you have a stack of papers, and so we've added a third dimension called depth, right? Depth. To find the volume, as you know, of like a cube or a prism, we're taking area. So we're taking area, and all we're doing is we're extrapolating it times a certain amount of depth. So conceptually, like I know for some of you this might seem like, wow, this is like second or third grade stuff, but conceptually this makes sense. And this is for the number sense that we're trying to develop. What we're doing when we're asking how much volume does something take up, how big is something, is we're saying, okay, there's a certain amount of area, and then there's depth to that area. So there's this much area times how deep it is, right? Now, imagine with me, we take this stack of papers, and I take half the stack and I give it to my friend Sadie. That was not half. Here, I had more papers than that to start with. So I take half the stack and I give it to my friend Sadie, right? And so now I have some pages, and then she has some pages, and this is how many pages. These are Sadie's pages, and these are Mr. B's pages. Now how much, so it's the same amount of paper. Now how does the volume work out? Well, we took the depth and we cut it in half, but the area is multiplied by 2, right? So the volume is the same. The area of each piece of paper never changed, but now I have the area over here plus the area over here times half of the depth of the original stack of paper. So come on, highlighter. So with this example, the volume of paper didn't change. It's just in 2 different spots, right? So what I did was I took the area. The area is now double. Just looking from this bird's eye view up here. The area doubled. The depth went in half. The volume stays the same because 2 times a half is 1, and 1 means no change, right? 1 is 100% of what I started with. 1 is no change. So try to think conceptually. Imagine you have a stack of, let's say, quarters. Let's see, you have coins that form little discs, and you stack them up. And let's say someone who's a real neat freak likes their coins stacked straight up and down. So they make a stack of coins and it forms a cylinder, and they calculate the volume of that cylinder, and they say, aha, the volume of this cylinder is this many quarters that I've got, American 25-cent pieces. Mr. Bourgeois does not give a fig about neatness or tidiness, and so his quarters are not stacked evenly. They kind of go, whoo-wee, but he has the same number of quarters. They just kind of bulge out of different spots, and his little tower, and you could play with coins like this, or poker chips, or whatever you want, and see, okay, so if I slide them, or let's say my stack of quarters kind of leans a bit, and I'm trying to see how far I can lean this thing before it falls over. And so my cylinder is leany, and Logan's stack of quarters or poker chips sitting next to me is nice and straight and orderly. We have the same volume of quarters, even though mine is slanty and has these weird angles going at it. We still have the same volume. We have the same number of poker chips or quarters or whatever we're doing, right? So that's really what we're going to be exploring in chapter 8. We're exploring how does it make sense of what volume is? What is volume? It's how much space the stuff is taken up. So whether your book is open or your book is closed, it's the same amount of paper. It's just shaped really, really, really differently, and becomes really kind of tricky and crazy hard to solve the area of an open book, which is this funky shape that we really never deal with. It's this, this thing that we drew, like seagulls in a Bob Ross painting or something. Happy seagulls. Happy birds. But then the closed book, oh, well, that's like a rectangular prism. I can solve that. It's the same volume. It's just one of them, it's easy because we have length times width times depth, and the other one, the shape changes. So as we explore these concepts, try to figure out why is the formula to solve the volume of a pyramid, why is it the way it is? And does it make sense? Because you can memorize formulas all you want, which is great. Memorizing formulas is fine and good. One ought to memorize formulas. However, I like it better if I really understand why the formula is what it is. If I can piece together, aha, this makes sense, that the area, or the volume of a cylinder equals the area of the circle. Oops, that was not straight. That's all right. The area of the circle times its height. Oh, well, that makes logical sense to me. I'm taking the surface, the area of the circle times how high the cylinder is, and that's my volume. Same as a rectangular prism. You're taking the area of the square, you're multiplying it by how many of those squares you got, right? Some symbol just showed up on my recording device that I had never seen before, and so I'm not sure. I wonder if my I wonder if my recording app is doing something weird. I hope I still have video. If I do this whole lesson and I don't have video, I might actually literally cry. All right, so cool. So I know I said page 120, and then I took their example and just kind of poo-pooed it, but I like my example better. As I think about stuff, as I think about the concepts in math, I like to find my own examples. That's the way I do it. So let's look up on page 121, Roman numerals CXXI. And we're going to consider, when we're dealing with three-dimensional figures, you're going to want all three dimensions represented, right? You're going to want the length, the width, and the depth. They're all going to be somewhere in your formula. So they start with a rectangular prism. They say, hey, if it's 11 inches high, and we know the volume is 275 inches, find the length of each side of the square base. Okay, cool. So how would we approach this problem on the top of page 121? So we've got a square. I'm going to start at the top. No, that's the eraser fire. This is a square, as best as I can do it. And they want to know, okay, so if it's 11 inches high, and the volume is 275 cubic inches, and it's hard to, cubic inches, whatever. Then how do we find the length and the width? So if you follow along, they know the formula is the volume equals base times height I don't like how they set this up, to be honest. It's not just, yes, it's the base times the height, but it's really three dimensions. It's the length times the width times the height. Length, width, height. So they use base. They combine these two into just capital B for base. You're free to do that. Feel free to do that. But we know that since this is a square, we know that the length and the width are the same, right? A square has the same length and the same width. So I'm going to simplify this. We know the height is 11. We know the volume is 275. So 275 equals the width squared times 11. So pause the video. Well, I guess the answers are right there in your book. So follow along. They say, okay, so we're going to divide both sides by 11 so that we have the width squared by itself. So divide by 11, and they get 275 divided by 11 is 25. So 25 equals the width squared. Which is equal to the base, the square inches of the square. So if you're just measuring the area, not volume, the area of this square right here, it's 25, which means it's a 5 by 5 square. So the length and the width of this square is 5 by 5. They kind of got a little nuts with the number sense on that one, in my opinion, for an intro problem. That's okay. Moving on. They want to do a quick check. We're going to pause. We're going to do quick check numbers 1 and 2. Pause. Quick check. number 1 and 2 on page 121. All right. If you solved them, here are the answers. The volume is 216 cubic centimeters, and the area, surface area of the entire cube is 200. Also, it's 216, but it's cubic. It's not cubic centimeters. It's square centimeters. What does that mean? So it says the cube is 6 by 6 by 6. Every dimension of this cube is 6. So 6 by 6 by 6. So if we take 6 times 6, we get 36 times 6 again. So 6, so the length times the width times the height equals 216 cubic centimeters. 3, that's a 3. Cubic centimeters. What about the surface area? So if you don't know what surface area is, it is the area of all of the two-dimensional, well, it is the how much area of paper you would have to use to completely cover the solid that you're doing. How's that? So we have this square right here. I'm going to do these dotted line things, why not? Actually, that should be a whatever. So we've got this cube. The cube is made up of a square on its surface right here, and right here there's a square, and on the bottom there's a square, and on this side there's a square, and on the side that we completely can't see there's a square. So 1, 2, 3, 4, 5. I'm missing a square somewhere. So top, left, right, bottom. Oh, and then the front. The front. Front, top, left, right, bottom. Front and back, top, bottom, left and right. 1, 2, 3, 4, 5, 6. There are 6 sides, and each side is a 6 by 6 square. So a 6 by 6 square has the area of 36 centimeters square. But there are 6 of those sides, so we take this 36 and we multiply it by each side, which is 6, and we're going to get, coincidentally, 216 centimeters squared. Not every figure is going to have a surface area that is equal to its volume. Beware. Here, this is the warning. Warning, because we're not doing a lot of angles anymore. I need to find a new use for Galaxy and Rainbow Pen. Or, nah, we're not going to change the color. We're going to keep Galaxy and Rainbow Pen. So beware. Not every cubes, yes, cubes will have a volume and a surface area that are coincidentally the same. Every other figure, rectangular prisms, pyramids, they could very well have volumes and surface areas that are different. Do not mistake the two. All right, what about quick check number 2? The volume of a cube is 512. Find the length of each side. We can work backwards, guys. There used to be a rap song by an old rap group called the Fat Boys. And they did a guest appearance on a math show, and they did a rap called Working Backwards is the way to solve your problem. Working backwards is the way, solve your problems. I watched a math show when I was a kid. I was that guy. It's true. Square One was the name of it. I would be curious to find out if they still have those available somewhere. Square One. I think I did look and I never found it. So if we know that the base times the width times the height equals the volume, base, width, or length, width, height. Let me do that. Length, width, height. I'll try to be consistent. Length times width times height. We also know that all the dimensions of a cube are the same. So the length and the width and the height are the same thing. So we could just call it the width cubed equals 512. This one you will probably have to do on a calculator, to be perfectly honest. I don't know that anyone really has the capacity to do a cube root on paper, and I really don't feel like teaching you at this season. I know there's a way, and I saw the way, and I learned the way at one point. I don't remember it still. There is a way to do a cubed root. I suppose the best way, if you don't have a calculator that can take, here's how you would do it. Do you remember how to use your calculators, guys? You take this and you raise it to the power of 1/3. And now if you don't have a 1/3 fraction function, then what you do is you take 1 divided by 3, take this answer of 0.33333333, store it in your memory. So memory plus, you push that button, and then you take 512 raised to the power of memory recall, and then that should give you the answer. But the answer is 8. You can also guess and check. You can also guess and check and say, okay, what's 6 cubed? Oh, I already know 6 cubed because I did that one up here. So it's got to be a little bit bigger. Let's try 7 times 7 times 7. Oh, okay, that doesn't work. Let's try 8 times 8 times 8. Oh, that's it. There you go. Or you could say 10 times 10 times 10 is too big because that's way bigger than 512. So let's go less. It's got to be between 6 and 10. So let's try 9. Let's try 8. Oh, there it is. That could be how you do it. Cool. So guys, this is one of those times when I really wish we were in a classroom together because this is really hard to do on a video. 3-dimensional figures. Are you kidding me? We're looking at the bottom, page 121. It said find the surface area of a square pyramid. A square pyramid has a square at the bottom, and then above it, they start building these thingies. So like there's like a square, and then on top of that square, there's another square that's a little bit smaller, and then another square that's a little bit smaller than that one, and then another square, then so on and so on and so on until you get up to this point where you just have a tip at the top, and it's not really a square anymore. It just comes to a point. So imagine square sheets of paper stacked atop each other, get smaller and smaller and smaller, and they form a pyramid. So the surface area of a square pyramid, you have 4 triangular sides that theoretically they would be equal. So 1, 2, 3, 4 sides of the pyramid, and then you have the square at the bottom. So the surface area is going to be the area of the square. Man, handwriting is hard. Plus 4 triangles, which should all be equal. I think cursive is easier. I'm going to do cursive. Triangles is. So check it out. They have find the area of the 4 triangles and add the base area and the area of the 4 triangles together. You'll find the surface area of the square pyramid. Turn the page. We're going to do page 122. Do that quick check number 3. Pause the video. Quick check number 3. Pause the video. Zoop, zoop. All right, unpause the video. Doodly doodly do. All right. A pyramid has a square base measuring 10 inches on each side. It has 4 faces that are congruent isosceles triangles. The height of each triangle is 13 inches. Find the surface area of the pyramid. The answer is 360 square inches. How do we get that? Well, we got the square. It has an area of 10 times 10, which is 100. The triangle is going to be 10 times 10, or excuse me, 10 times 13 divided by 2. So 130 divided by 2, because you take 1/2 the base times the height, not 12. So that would be 65. And we take that times 4 triangles. And that will get us to 360 square inches. Cool? So 4 triangles. Make sense? I think it does. If it doesn't, message me. Send me a note. I have to blow my nose, sorry. All this cholera is getting to me. Okay. So, all right. Circumference of a circle. Paper plate has a diameter of 9 inches. We're still on page 122. Use 3.14 as an approximation for pi. Sweet. You can also use 22/7. That's a really good approximation for pi. Find the area of the paper plate. All right. So the formula for area is pi times r squared. Pi times r squared. is the formula for the area of the paper plate, or the area of a circle, pardon. Assuming the paper plate is a circle. So they give you the diameter. What's the diameter? The diameter is the widest part. The radius is 1/2 of the diameter. So guys, if any of you are behind on your terminology, you'll need to get caught up. So this is the diameter. Diameter. 1/2 of that is the radius. The radius is 1/2 of the diameter. Cool? It's the point, the radius is the point from the very center of the circle to the edge, and the diameter is a line that goes, straight line segment that goes from edge to edge and passes through the center. So it's double the radius. The area is pi times r squared. So if the diameter is 9 inches, that means the radius is 4.5. 4.5 times 4.5. I will let you use your calculators. 4.5 times 4.5 times pi, or 3.14. It will equal all this junk right here, 63.585. Inches squared. Label our stuff. Groovy. What's the circumference? The circumference is pi times the diameter. I feel like I should be using colors. This is the formula for area. Circumference is like perimeter. It measures the distance all the way around. So circumference equals the diameter times pi. Some people write, I've seen the formula for circumference written as 2 pi r, so 2 times pi, which is, I feel like, confusing because the diameter is the same as 2 times pi, so you could just say diameter. So you just take pi times 3.14 and you go with it. Let's just do quick check number 4. Quick check number 4, guys. Pause the video. Do quick check number 4. Groovy? Unpause the video. So it says number 4, find the circumference of a waffle. The waffle is a circle with a diameter of 6. I gotta say, I'm drawing pretty good circles. Everything else I'm doing on this whiteboard is garbage, but my circles aren't bad. Let's see, circumference of the waffle. Sorry, the diameter is 6. 6. Take 6 times pi, you get 18.84. That's A. Circumference. To find the area of the waffle, we take pi r squared. So pi times 3 squared. 3 squared equals 9. So pi times 9 equals the answer of 28.26. Oh, guys, if you're not already listening to me on like double speed on your listening device, if you're watching me on YouTube, for goodness sakes, put me on 1.5 times speed. There's a way to do that. I'll talk faster. It'll be great. You'll get through your math much faster. And then you can always slow it down or rewind a bit if you need me to, if you need to see that again or hear that slower. By all means, slow it down. Hit pause and digest what I just said. These are things you can't do in a classroom. Let's take advantage of the advantages. So this, I lament the disadvantages of video format, but by all means, take advantage of the advantages that you can rewind me, you can pause me, you can make me sound like a chipmunk. Like, do the things that like, take advantage of all of the benefits of using video format. You can even listen to me at times 2 speed on your listening device. If you download the video, your video player, your mileage may vary on your video player, but for goodness sakes, if you haven't already been doing that, I highly recommend it. You'll get through math faster or slower, however you need to. Yeah, it's great. We're turning the page. 123. Yeah, 1000, no, 123. So, look at these figures. I don't want to draw these too quickly, but look at the figures. They say identify the net. So if you took this piece of paper, this is very visual stuff, which I love. I love the visual stuff. So name the solid that each net forms. So you see that first one? If you folded out each of those dotted lines, what would you have? You'd have a cube, rectangular prism in the second picture, a triangular prism. In the third picture, you have a triangle, and it extends a long ways into this other triangle dealy. A triangular prism. That's pretty sweet, if you ask me. You didn't, I know, but if you did, that's what I would say. It's pretty sweet. And then there's a square pyramid shown there. You kind of have to visualize the sides of these pieces of paper getting folded up or towards the center, I guess. Quick check, do the quick check 6. Pause the video. All right, do the quick check. Quick check 6. A is, wait, how does this go? Yeah, A is, wait, what? I'm confused. A is a rectangular, should be a rectangular prism. B should be the square pyramid, and then C should be that triangular prism jobby. I'm not sure what the answer key is trying to tell me. We're going to skip it. Guys, we're on page, let's turn the page to page 124. Pretty sweet. All right, so the object of this lesson is to recognize a cylinder, a cone, and a sphere, and the cross sections of solids. Cross sections, you guys, this is going to get real. Okay. There's a vocabulary box. Check it out. Cylinder, cone, lateral surface, slant angle, sphere, hemisphere, plane, cross section. Pretty sweet. So check it out. A solid cylinder has a curved surface and two parallel bases that are congruent circles. Congruent circles. The radius of a cylinder is the radius of one of its bases, says enthusiastic math student. The height is the perpendicular distance between the parallel bases. So notice it says that they're parallel. That's important. So this circle is parallel to that circle, which means if you extend out a stick, if you took a stick or a tape measure and you held it level on that surface, let's do this. All right, and you had another tape measure going out that way, they would extend forever and ever and ever without ever touching, right? Parallel, just like parallel lines. They have to be parallel and the circles must be congruent. Otherwise, the math becomes really tricky on calculating its volume. So, a cylinder has some things in common with a prism. The bases are circles instead of a polygon, and the cylinder has a curved surface instead of a flat surface. So the weird part about this is that it goes around. A cylinder has a curved surface. Look at the net shown at the bottom. There's a rectangle, which you would curl up. So if you uncurl this curled surface, you get a rectangle, and then you'd have a base and then a base. I'm all about that base. No trouble. Cones. A cone. We're now on page 125. 125. A cone, you guys, different than a pyramid. A cone has a circle base, comes to a vertex, comes to a point, and it's got this lateral surface thingy. Look at the picture in your book. It's better than what I'm about to draw. They do this like a dotted line. Woo! So here's where we see a lot of these points. So you see it looks kind of like a dunce cap. So this is, back in the olden days, they would shame you if you did something wrong in class by putting a conical hat on your head that says dunce. It means you're a dummy. We don't do that anymore because that wouldn't be nice to, I'm not even going to say a name. I was going to say someone's name, and then I'm like, I don't know if they would take that well. I suppose it depends on the person. Anyhow. Oh my gosh. I highly doubt Mrs. Britsky would allow me to reinstitute the dunce cap. Well, maybe in 10th grade we'll do it. I'll ask. Anyway, so look at that. So you notice that the distance between there's a radius, there's a circle down here, right? So it's got a center point and a radius, and the radius to the height will make a right angle. So there's a perpendicular that leads all the way up to the vertex. And the angle, let me draw a fresh one over here. So this is going to form an angle, right here. There's going to be an angle. Yeah, it's going to be look like a triangle from the side, even though this is a curvy surface. It curves around, right? Like a birthday hat or a dunce cap. Then look at the net at the bottom. So they give you two different measurements right here. They give you the height, which is going straight up from the bottom to form a 90-degree angle. That's just the height. The slant height is the length of that side. That's going to be important. This is the slant height. Cool? Look at the net at the bottom. Enthusiastic math student says slant height is the distance from the vertex to any point on the circumference of the base. There you go, slant height. And then enthusiastic math student on the bottom says the net of a cone has this weird curvy thing and then the circle for the base. Weird curvy thing is like, you know, what they just showed you right there. All right, turn the page, y'all. All right, so I was reading this note to teachers that I missed the first time I went through this. Sorry for the pause. Goodbye, dunce. Sweet. So a sphere has just one big old curved surface. Notice how on the previous 2 pages they showed you the net. So like if you unfolded, took apart and made it into a 2-dimensional thing, that it would form some flat piece of paper that you could fold up into a triangular prism or a rectangular prism or something like that. The sphere really doesn't have anything like that. Sphere is really hard to make a map out of, like the whole globe, because you just can't do it. It's all curvy and there's no flatness on it anywhere. It gets crazy. If you observe, so like meditate on the reality of what a sphere is. It's like a ball, right? If you slice a sphere in half, you get 2 hemispheres as shown. The distance from any center point to its surface is called the radius of the sphere, right? Similar to a circle. I did it again. Come on, circle. This is a circle. You find the center, you measure to the edge, that's your radius. If we make this a sphere, where this is, hello, 3 dimensions. Not really. You can't see it, but there's a 3rd dimension here. You can draw the radius and go any which way from the center all the way to the edge in a straight line segment. That measurement will be the radius. Sweet? A cross section of a solid. Supposing we take just a slice out of a three-dimensional figure, any kind of a solid. We take a slice out of it. That would be called a cross section. They're gonna identify some very, very abstract things. They're gonna define some very abstract terms right here. So read that bottom blue box. Identify cross sections of solids. A plane. Let's get real here. A plane is a flat surface, two dimensions, that extends infinitely out. When a flat plane slices through a solid, the result is a cross section. If you ever watch any of those weird cartoons, stuff like Transformers or Ninja Turtles or any of those kinds of weird cartoons, they always talk about from another dimension or from another plane. Like a plane in mathematics, it's like, okay, let's define this as a state of existence. Things exist in this plane, and we're going to identify them. Like one sheet of paper, as I'm doodling on it, is one plane. Theoretically, it's not a plane because it doesn't extend infinitely out. It doesn't have a width and a length that are infinite. However, you can kind of think of it like a plane. And then you can do a lot of weird math when it comes to like, what if another sheet of paper intersects it at an angle? Then things just blow up. It becomes really cool and really advanced engineering, mathematical, theoretical stuff. It becomes very difficult because in real life, we don't interact with planes in that same way. We have like a universe that we deal with. We have, outer space in the galaxy, which is like, I don't know, it gets weird, you guys. Planes get weird. It's very abstract, and I wish there was a way that I could convey it to you that is super helpful to understand what it is. Especially because your book is two-dimensional. The content of your book is explained in 2 dimensions, and so visually planes are hard to see. But let's see. So if as a plane slices through something, if a plane slices through the Earth at the equator, it would divide in northern and southern hemisphere. And then we could all right, cross section. These are vocab words that we're going to deal with in this whole chapter 8 stuff. Cross section is a 2-dimensional slice of a solid. That's what it is. I don't think that northern and southern hemisphere discussion that they do is very helpful. I want to do something different. Look at page 100. So if there's a 2-dimensional slice of a solid, let me define this a little bit better. They say that if you take a slice, imagine a sphere. Let's start with this. Imagine I have the globe. If you have a globe, look at it. If you have a ball, a basketball, look at it. Then imagine that a plane slices through your globe anywhere. It can just take a tiny little slice off of the edge. That would make a small little circle, right? Or if you slice clean through the ball so that it cuts through any point of the center. If it cuts through the center, it has to cut through some interior piece of the sphere. That's what's important. It has to somehow go through the interior of your solid. So in this case, the sphere. If it cuts through one of the, do you guys remember the great circles? You've got the lines. I'm going to slide down here a little bit. We've got the world, right? We've got these lines of latitude. The lines of latitude, so there's the equator. The equator is the biggest line of latitude. Every other, like the Arctic Circle and the Antarctic Circle, they're the tiny ones. The meridians that slice through both poles, the North and the South Pole, they are all the same size, and they're the same size as the equator. I feel like that's a helpful way to visualize a plane slicing through, creating a cross section of the Earth, right? The problem is, the hard part to wrap your mind around is the cross section is 2 dimensions, which means it has no depth, it has no thickness. So if you take a slice out of the Earth, realistically that's going to have depth to it. It's going to have some amount of thickness. A 2-dimensional plane has 0 thickness. It exists only in those 2 dimensions. If you try to describe it in terms of thickness, you've added a 3rd dimension to the conversation and you broke math. You can't do that. Don't break math, you guys. It's all I have. It's all I have. If you break math, I'll be a nothing teacher. Okay, enough of that. Look at page 127. We'll just do this. Now we'll do this. No, we'll do this. They say to make these things out of clay. I don't want, we're not doing that. Guys, I hate arts and crafts. I hate cleaning up messes. I hate getting stuff out and setting stuff up. I hate stuff like this. If you want to do it, by all means do it. But they say make 3 clay cubes and then make a cross section parallel to a face. You can just visualize this. Scratch that. You can just visualize this. If you have a perfect cube, right? You have a perfect cube. If you make a slice that's parallel to one of the faces, I'm going to kind of go here and slice this down. What shape did I make? I made a square. Sweet. What happens if I slice from this edge right here all the way over to this edge? What did I make? Not a square, but a rectangle. You see that? It's going to be a little bit longer on this bottom side because I'm going across the diagonals. I'm taking a square and I'm cutting it into 2 triangular prisms. Now let's take that same cubey thing and let's say I just slice off a corner. What cross section did I make? Let me try that again. I slice here, I slice here, I slice here. My cross section, my plane, the imaginary plane that slices through the universe, just made a triangle shape. It's pretty cool. There, I condensed like 45 minutes of work into, are these the same color? This is driving me crazy. Are you serious? That's green? All right, if you say so. All right, page 128. Let's identify the cross sections of a square pyramid. Guys, I'm sorry, I spoiled this for you. I imagined a pyramid as stacks of paper that are getting smaller and smaller as they get up to the top until you end in just a little dot. But look, if you take the cross section and slice a piece out of the middle of a pyramid, you'll get a square. If you take it depends that depends. If your cross section is parallel to the bottom, try again. If your cross section is parallel to the bottom, you'll get a perfect square, right? I can't do the dotted lines very well. If you take a cross section that goes through the vertex, right there, you'll get a perfect triangle. As long as your cross section is parallel to the base, you'll get your cross section should be the same shape, only smaller, as your base. If you cross through the vertex and part of the base, you're going to get some kind of a triangle. Now, if you cross, you can always cross through a pyramid, like do a wonky cross like this and get some other kind of wonky shape. but I doubt they'll do that to you on a test. We'll see. Cool. Look at example 1. A plane slices a rectangular prism parallel to its base. The cross-section would be a square. Yeah. Oh, it says tell what cross-section is formed when a plane slices. A plane slices through a triangular prism. So now we're on page 129. Green, allegedly. I need to see red and green next to each other. It's driving me crazy. Yeah, I don't see it. Okay. So a plane slices a triangular prism parallel to its base, your cross-section is going to be a triangle. And if a plane slices a cube perpendicular to its base, so it forms a 90-degree angle, the cross-section is a sphere. Guys, we could do the guided practice. I'm just gonna, okay, pause the video, do the guided practice 1, 2, 3, and 4, and then we're gonna do something else real quick, okay? All right, here are the answers. Number 1, the cross-section is a rectangle. Number 2, the cross-section is a rectangle. Number 3, the cross-section is a rectangle. Number 4, the cross-section is a triangle. They show you the cross-section, and so I don't understand why that's hard. But if you're not visually inclined, and those were difficult for you to see, then maybe you should try to get some shapes together and imagine cutting slices, or actually get some Play-Doh, try to make shapes as best you can, and then take like a piece of wire or I think that's the only way you can cut Play-Doh really reliably is with wire, and then slice a piece off and see what shape is made by the slice. But look at the think math. This is really hard. I don't know. This is really thinky. The think math in the top corner, it says, do all cross sections of a sphere form a circle, and are all of the circles congruent? And explain. Imagine a sphere and think, is there any way, as I think of the globe, are all the cross sections going to be a circle? If you have a plane, the plane can't be bendy. We're not doing bendy planes now. It's got to form a two-dimensional shape. As I'm thinking about it, I know every single plane, as it slices through a sphere, is going to be a circle. Are they all going to be congruent? No. You're going to get smaller circles, right? The Arctic Circle is smaller than the equator, as I've already demonstrated, but they're always going to form a circle. I can't think of any way that you're not going to get a circle. If you disagree with me, I defy you to show me. Show me a cross section that cuts through a sphere that does not form a circle. All right, guys, video over. Good job. Do your homework. I love you. Stay safe. Be well. Blessings to everybody.